All right, gang, Mess 6610. Let's get the oh, I don't know which one we want to do. The dual credit. Yeah, let's just drag it over here and open it up. All right, so it looks like we have group and gender. So it's been a while, so let's dive in and see what group looks like. So it looks like a on-campus class maybe versus a dual credit. And let's dive into gender. Looks like we have 400 females and 400 males. All right. So then it looks like we've got a sample size of 800. Uh, let's just go ahead and run the model for the two-way. So I want points over group by gender. All right, cool. So we have again we get tunnel vision on group by gender. So I really don't care much about the main effects at this point. And again, just to review, if the if the interaction effect is not statistically significant, I would rerun the model with only the main effects group and gender. But since the interaction is statistically significant, it has my attention. So a couple of plots that I may want to take a look at. I kind of like to look at side-by-side box plots, and turns out that the points over group by gender is pretty interesting to look at. Now you'll see that the heading is missing, so I think if I extend it out a little bit, we get. So what I can do here, first of all, keep in mind that we're examining means, and box plots don't give means, but they give medians. So the dark line right there is the median. But when we have a relatively symmetric distribution, the mean and the median are going to be about the same value. So that value there, 148, whatever it may be, is the median. But because I have a relatively symmetric distribution here, I can assume that the mean is going to be very, very close to that value. So the very first thing I have is I start looking at the relationship just across uh, campus and dual credit. And I'm assuming we're going to have statistical significance there. And campus and dual credit for males, I assume we have statistical significance there. Next thing I do is I try to imagine combining the females just to get a difference between, uh, or to get a combined measurement, and combining these over here and get a combined measurement. And then I would want to kind of visualize combining the dual credits and getting a distribution there. It's kind of hard to visualize, but again, we got the fallback over here with our F statistic and p-value. So again, this is something that you would want to report. Interaction plot, there are a lot of ways to get interaction plot. Okay, there you go. Just a lot of ways to do this. You can use the PPUBR package to get some much more attractive plots. This interaction plot command gives you just kind of the bare bones. So it's really hard to determine which goes first for X factor. I like to create both, and I'll demonstrate that to you here in just a second. So my X factor is group, and then I want to trace factor to be the other independent variable. And then my response here is just going to be the points. And I want the function to be equal to the mean. All right. So if I run that, I get some warning messages. I really have no idea what those are, but I see no reason for a warning. Um, and I can see that the lines are non-parallel, not by much, but non-parallel, and that the difference from here to here is about the midpoint there. The difference from here to here, there's the midpoint. That difference is statistically significant. Come to the center of this line, get the mean of female. Come to the center of this line, get the mean for male. That difference is statistically significant as well. Now, I always like to switch these just to see which plot gives me the most information. And I don't think either one is that drastically different than the other. So anyway, there's just kind of food for thought. All righty. Now, what we have here is we have kind of an interesting situation. So what I want to do to motivate, I want to get ready to demonstrate to you, is I want to go back up to our model, and instead of having group by gender, I want to do gender by group. So I want to reverse the independent variables. And when I do that, you'll notice that even though the ordering is different, that the F value, the F statistic for group is the same. The F statistic for gender is the same. And the reason this is the case, without diving too much into a rabbit hole here, by default, what R uses is called a type 1 sum of squares calculation method. It's kind of equivalent to a hierarchical regression where you put one predictor in your model and then you add another predictor and you kind of analyze the change in your model. That's kind of what's going on here. It will calculate the sum of squares based on group and then gender being added. Down here, it will calculate the sum of squares based on gender in the model and group being added. Now, if you want to control for that, you can do what's called a type 3 sum of squares calculation in R. Now, pretty non-entertaining if we have a balanced design. But let's say that, I'll tell you what, let's manipulate our data. Um, so I really wish I had a smaller data set. I'll tell you what, let me grab a different data set. Let's go to the two-way ANOVA. I think this is going to be a better illustration. All right, so length of this is just 18. Okay, cool. Well, let's just look at the entire data set since it's very small. Now, I have so table A, I have 9 and 9. Table B, I have 6, 6, and 6. So I have a balanced design here. So I want to mess that up, okay? So I'm going to subtract a few rows and create another data set. So I'm just going to call this data 999 for lack of anything better. And I want to take new data, which is the name of the data set I'm going to tinker with. And then I want to subtract some rows. Now this command allows me to manipulate rows and columns. So I'm going to go ahead and keep this a blank because I don't want to manipulate the columns at all. I just want to manipulate the rows. So I want to subtract one of the A1, B1s. So I'm going to subtract row 3. And I want to subtract one of the A2, B2s. So let's subtract 11. All right, so I should attach data 999, and then I want to look at data 999. So when I do table A, I get 8 and 8, but when I do table B, I get 5, 5, and 6. Okay, so I don't have a balanced design anymore. Now, the reason I want to show this to you is if I run a model on AOV Y for A cross B, notice the F statistic that I get for A, B, and the interaction. Now, if I reverse the order, notice that I get different values. It can drive you crazy. Now, notice the interaction will stay stable. The type 1 sum of squares calculation method R uses will not impact the interaction, but it will impact the main effects. And quite interesting, this is a really cool example because you can see that if group B is entered first, then both main effects are statistically significant. But if group A is entered first, wow, this is just great. I couldn't have come up with this on my own in a million years. Uh, and I'm just really glad this happened. Then group A is not statistically significant, but group B is. So it completely changes the dynamics of your result.